VLSos here. This is a video lesson on continuity, both the informal and formal definition. To practice and talk about continuity, I'm going to draw a piecewise function that's going to have many features that we can analyze regarding continuity. We're going to have a piece that reaches a vertical asymptote. There's a hole, then a closed dot, and the function jumps to another hole and continues, reaching a hole that has a closed dot at a different value, and then continues. We're going to highlight areas in the domain where these features exist. At A, there's a vertical asymptote. At B, there's a hole. At C, there is a jump. And at D, there's another hole, but it has a value. What do we mean by continuity? Previously, in a course before pre-algebra, typically, pre-calculus, continuity was the idea of being able to draw a function without lifting your pencil. So if we were drawing this function, we would have to lift our pencil in several different places. We'd have to lift our pencil at A to continue. We'd have to lift our pencil at B momentarily, and then at C and D as well. At all of these places, A, B, and C, we have a place of discontinuity. The function is not continuous. Informal definition, discontinuous where you must lift the pencil to draw. We needed an informal definition so that we can talk about this important feature. We're now ready for the formal definition of continuity if we've been introduced to the concept of the limit. The formal definition is a function is continuous if at A, three rules apply. 1, the value exists. F at A exists and can be found. 2, it'll be continuous at A if there is also a limit as x approaches A, and that limit exists and can be found. And 3, the third thing must also be true, is that the value at A must equal the limit as x approaches A. This is a little bit shorthand for the formal definition. If it was written in a textbook, it would be much more complete with the language that was being used in reference to the symbols. The shorthand, this could be expressed even more concisely by these three rules being the concepts that there must be a value at the place, a limit at that location, and the value and the limit must be equal. So we can say now precisely why at each of these locations A, B, C, and D, it is not continuous. At each of these locations, at least one of these rules is broken. At A, there is a vertical asymptote. We look to see if there is a value, a limit, and that the value and the limit are equal. The first rule is broken at A, there's no value. If we put whatever number A is into the domain, it would produce something that doesn't exist. That's why there's a vertical asymptote there. But it is not, this function, if we called it f, is not continuous because there's no value. And rule 3 can't work either. If there's no value, then it couldn't be equal to the limit. At B, we also have no value. There's an open dot. The function is not defined at B. So it's the same reason the function is not continuous at B because there's no value. But the behavior of the function at these two places is different, even though it is not continuous for the same reason. At C, there is a value. It's the closed dot. But there's no limit. We have a left-sided limit and we have a right-sided limit, but there's no absolute limit because the one-sided limits are not equal. So the reason why it is not continuous at C, no limit. One-sided limits are not equal. And at D, we have a value, it's the closed dot. We have a limit because the left and right sides limit to the same place. It has the same one-sided limits. So the absolute limit exists, but the limit and the value are not equal. So it is not continuous at D because the value does not equal the limit. Now, though I've talked about and introduced the formal definition of continuity, if we were to, what I've done here is I've answered the reason why f is not continuous kind of in a shorthand manner. If I had the function or the expression for it, and these places in the domain were not general but at specific values, then I would need to do a little bit more to show what the function values are, show what the limits are, and then show why they're equal or not equal. So I would need to express my answer a little more thoroughly when working with an actual function expression and values. What I've presented here is a quick way to introduce the concept.